In the previous video, we talked about ideal transformer. Ideal transformer is nothing but where there are no power losses. Okay, power losses are zero, and primary secondary has infinite impedance to zero resistance. Total supply energy will be transferred to the secondary. And on before video, I talked about k equal to m over square root of L1 and L2. M is the mutual inductance, L1 and L2 are the inductance of coil 1, inductance of coil 2. K is called coupling coefficient. K value is between 0 to 1. 1 is excellent, so the coupling between two coils is good. 0 is there is no coupling. Okay, this is about ideal transformer. Now I also wanted to talk about linear transformer. The transformer said to be linear if the coils are wound on a magnetically linear material. Okay, below circuit shows the equivalent circuit of linear transformer. So linear transformer is basically if I increase the I1, I2 is going to change in the same ratio linearly. That's called linear transformer. Okay, when it comes to the practical transformer, here is the equivalent circuit of practical transformer. In reality, the coil 1 is going to have resistance. We know that R equal to rho L by A. Every coil will have some resistance. So this is the resistance of coil 1, primary coil. And here is the resistance of secondary coil. And X1 is inductance of the primary coil. X2 is the inductance of secondary coil. So these coils' inductance are shown in figure. So these two lines indicates that that's ideal transformer. This GC, also called basically R core, resistance of the core. Okay, G is called conductance. Sometimes we indicate with either RC, sometimes conductance. GC doesn't matter. Usually I'll go with RC. RC, very big number. That's the resistance of the core. And here XM, basically reactance of core. Okay, B is susceptance, opposite to the reactance. So don't worry about G and B, RC and XM. This is the practical transformer. Okay, we're not going to do any practical transformer examples in this class. Probably you're going to learn that in 488 class. In the previous video, we learned about reflected impedance and input impedance. Here, I'm going to solve an example based on the reflected impedance and input impedance. So here, the given values are, he gave us the mutual inductance, L1, L2. Actually, everything is in ohms, so mutual reactance, self-reactance or L1, inductive reactance, and some R1 and R2 and the load impedance. So reflected impedance, this is the formula for reflected impedance, omega m square over R2 plus ZL plus j omega L2. So basically what we are doing here, we are converting this whole secondary part, moving it to the primary side. So I end up with reflected impedance as 0.185 minus j 0.169. So basically what we did here, this is the formula I derived in the previous video. Please go through the video. So here I have a source R and JL1, which is J8 ohms. Now I have reflected impedance ZR. This ZR is nothing but equivalent of the secondary resistance after moving to the primary side. That's called reflected impedance. Okay, so I found the ZR. Now the input impedance is nothing but the total impedance looking from the input terminals, R1 plus j omega L1 plus ZR. That will give you the input impedance. Okay, based on that input impedance, once I know input impedance, I can find the current. I equal to V1 over G input. V1 is given 40 at an angle of 0, and Z input we just found that 4.185 plus J 7.831. So I1 is the total current supplied by the source in the loop 1. Okay, this is how we can find current by using reflected impedance and input impedance. I'll stop this video here. Next video I'll continue with transformer ratios. Thank you.